ايه الطاقة.
Who's there? Okay.
Sir,
Yes.
can you give me permission to record it?
Yes, of course I will. Just let me get the admission for all of you, and then I'm going to give you the permission.
Even before now, I didn't have it, sir.
I'm going to give you mine. Don't worry.
Okay.
Sir.
Okay. Let me check it. Let me check it for you.
Sir,
Yes.
sir, where do we use the Divisivity equation? I mean, like, for what?
Oh, actually, we do not use the Divisivity equation. Who is talking to me?
For what, sir?
But we do not use the Divisivity equation directly. We use the solution of the Divisivity equation. See what I'm saying? I mean, now we are talking about the Divisivity equation, but in reality, we are looking for the solutions of the Divisivity equation. See what I'm saying?
Yeah.
All the mathematical models used in reservoir engineering, production engineering, all of them comes from the solution of the Divisivity equation. See what I'm saying?
Yeah, yeah, okay.
Now, for well-test analysis, we're going to work directly with the solutions of the Divisivity equation, and we will see. So now, I think probably the next half an hour, we're going to finish talking about the Divisivity equation, and then we're going to go to the solutions of the Divisivity equation. Okay?
Okay, sir.
Okay. I'm still waiting for the save the records. Now I got 26, so we will be fine. Okay. Just remind me to save everything. Okay, I will do that again. Okay, guys, let me share my screen again with you. Okay, so here is sharing my screen. And now I'm going to give you the permission, all of you guys, to record if you would like. Ahmed, okay, you got the record.
Yes.
Furat, you got the permission. Lawan, you have the permission also. Mateen, you got the permission. Muhammad, you got the permission to record. And I got, who is that? The last one? I don't know. Who is that? Okay, all of you. Okay. So now I've been talking about the hydraulic diffusivity here, this model, as you can see, and what we have the transmissibility, we have the storadivity, we have these two, things. Okay. Okay. Now, in the divisibility equation also, there is CT. That is the total compressibility. Total compressibility. This is CT. See, guys, here is CT, total compressibility. CT, if you have multi-phase flow, can be calculated from what? From the compressibility of the reservoir fluid, that is oil times saturation of oil, gas times the saturation of gas, water times the saturation of water, and the compressibility of the solid material. So basically, we will work with C sub T. Okay. And what I'm talking about well test analysis, we don't look for how much COSO, how much CWSW, how much C gas as gas. We are looking for CT there almost. And as you can see, here is the compressibility of the solid material, and here is the compressibility of the solid material. Comes from this model, or sometimes it could be calculated by this model or that model. Okay, do not focus here that much. This is not really important. Okay. Oh. Now, Farat, you have asked me about the divisivity equation. Okay. Let us get back here. This is what we are looking for. See, guys, this is what we are. Give me your attention, please. This is what we are looking for. This is our target. This is our divisivity equation. See, guys, this is our divisivity equation. So let me cut this one and bring it with us. Let me cut it so it would be better. Okay. Okay. Let me remove this one and put it down so you could see this one. Okay, it does not come. Okay, okay. Guys, what we have here, we have R. See, this is R, this is the radius. Radius. Radius of what? Radius of any point in the porous media. I mean, I'm talking about the distance from the wellbore to some point in the porous media. So R is the distance or the radius from the wellbore to that point. Now, we need to change this one. We need to change this model. This is the divisivity equation here. We need to change this one from real-time parameters. These are real-time parameters to dimensionless parameters. Have you used dimensionless parameters before, guys? Have you used dimensionless parameters before?
No, sir.
Okay.
Sir, parameters with no unit, right?
With no unit, exactly, with no unit. You do not need to put some units here. Now, why we need to do that? Why we need to move our divisivity equation from real-time parameters, that is R, fit, pressure, PSI, CT1 over PSI, T, hours, K, millidarcy, to dimensionless parameters. Okay, the reason for that, we need to make it more universal. I mean, we need to have the divisivity equation with universal application. It could be applied everywhere because it does not have units, so it could be applied for all reservoirs. Now, to do that, we need to change some of these parameters. Like what? For example, we need to move R from the concept of the distance to some point at the porous media to the concept of dimensionless radius or dimensionless distance. The distance measured based on some other reference distance. What does it mean? What does it mean? Okay, let us say that we have RW is the reference distance. What is RW? Wellbore radius. Do we know the wellbore radius? Of course, we know the wellbore radius. How much? Basically, let me say that 0.5 inch. 0.5 feet, for example. Sorry, 6 inch. So it is 0.5 feet. So we know RW. Now we can define the distance to the point in the porous media using the reference distance of the wellbore radius. So for example, we can say the distance is 100, which means that the distance to that point, 100 divided by 0.5, this is going to be what? 200 feet. So what I'm saying? So R sub D, it is dimensionless radius. R sub D, this is R sub D. This is called dimensionless radius. What is that? R, the distance at any, the distance to any point in the porous media, divided by RW. So if RW 0.5 and R is 100, then R sub D going to be what? 100 divided by 0.5, this would be 200. But we're not going to put fit. We're going to say 200 only. Is that clear so far, guys?
Yes, sir.
You have to memorize, please. You have to memorize these parameters. One of them R sub D. What is R sub D? You have to know it is R divided by RW. So what I'm saying? And what is the second? T sub D. What is T sub D? Dimensionless time. Again, what is dimensionless time? It is the time defined by a reference time. See what I'm saying? It is the time defined by a reference time. In this case, T sub D, dimensionless time, see, it is 0.002637 K times T divided by 5 mu CT RW square. It is just like this is your real-time T, see, and this is your reference time. See, we can understand like this. This is your real-time T, and here is the part of the reference time. That is 0.002637 K divided by 5 mu CT RW. It is taken from where? If you look, if you go back to the divisivity equation, you're going to find this part comes from where? From this part here, see? See, this is the part here from 113. Of course, I'm talking about reciprocal of the term in 113. So please memorize T sub D. And what is the third parameter? The third parameter is B sub D, dimensionless pressure. What is dimensionless pressure? It is the pressure, real pressure difference, defined by a reference pressure difference. You know what I'm saying? And this one is KH divided by 141.2 Q nu delta B. See, this is delta B. Bi minus the pressure at any point. Pi minus the pressure at any point at any time. Please take care of these three models. Take care of these three dimensionless parameters because we're going to use them many times. It is very important to understand the solutions of the diffusivity equation, knowing very well these three parameters. See what I'm saying? So please take care of them. Now, I need you, all of you guys, I wish if you could do it. Knowing that we have these three parameters, how can we move? See, how can we move? Guys, listen to me. If you can do it this week, how can we move from this shape, see this shape here, to that shape here? See, this one is the same. This one, see, it is the same diffusivity equation, but in dimensionless parameters. It is the same for that one. So 113, 1111, both are the same. But one of them is the diffusivity equation in real-time unit, and the other one is the diffusivity equation in dimensionless parameters. Now, can you please move from this shape to that shape? Can you please do it? I mean, you can do it mathematically. My question is, can you do it mathematically? Using what? Using the three parameters here. You have this week, or not this week. I mean, you can give me some feedback before our next class. This would be Wednesday. See what I'm saying? If you need my help, you can contact me. I need you to answer the question, how can we move from this shape to that shape using what? Using these three equations. Okay? Good. Okay. Now, we're gonna stick with this one. So we're not gonna talk about the first one. We're gonna talk about this one. We're gonna talk about this one. See, here is the model. This is the diffusivity equation. This is the diffusivity equation in dimensionless form given to us for circular drainage area. This is the diffusivity equation in dimensionless form for circular drainage area. Now we need to solve this one. Now, in well-test analysis, we have three solutions for the diffusivity equation, depending on the wellbore type and reservoir geometry. We have three solutions for the diffusivity equation, depending on what? The wellbore type and the reservoir geometry. The first one is called point source solution. The second one is the line source solution. The third one is the plan source solution. Now, for our case, what we have? We have the vertical wellbore. See, this is our vertical wellbore. See? So this is our vertical wellbore, see guys, inside the porous media. And this is our wellbore, see? See? So the fluid is going to be like this. Here is the direction of a flow. Now, can we assume that the wellbore radius, of course, you know, guys, wellbore radius does have some impact on your production. As much as you have bigger wellbore radius, as much as you could expect to have more production or less pressure drop. Yes, of course. Now, for the mathematical purposes, we can assume that the wellbore radius could reach very small value, infinitesimal. It's called infinitesimal value for the wellbore radius. So instead of having like a cylindrical shape, we could have only the line. Where we can consider the wellbore radius just a line somewhere in the porous medium, and the fluid is going to move toward this line, and this line does not have really the same radius of the wellbore. This kind of assumption again. So in this case, we're going to assume that the wellbore radius is going to reach infinitesimal value, where we could imagine that the wellbore radius, instead of having a cylindrical shape, we will have only a line inside the porous media, and the fluid is going to move toward this line. This is called the line source solution. And the line source solution gonna give me, this is the line source solution for what? For the divisivity equation. Which one is this one? Given by equation 1111. And here is the solution. See, this is the solution, guys. See, here is the solution. So this is the solution of what? This is the solution of the divisivity equation for, as I said, this is for circular drainage area using the line source solution. And of course, this is for oil, single phase flow, homogeneous isotropic formation. So the solution says that the pressure in dimensionless form, again, the pressure in dimensionless form, this is the pressure in dimensionless, at any point R sub D, at any point in the porous medium, R sub D, and at any time T sub D, dimensionless time. Again, when I say PD, I'm talking about dimensionless pressure, but it is pressure. RD, this is dimensionless radius, this is radius. TD, dimensionless time, but it is T. This would be given by minus half EI RD squared divided by 4TD. This model says that the pressure at any point, at any time, can be calculated by minus half EI function RD squared divided by 4TD. Now, guys, do you know what does it mean, EI function? How can we calculate EI function? Have you heard about EI function before? EI function.
No, sir.
Okay. EI function, actually, if you Google EI, you're gonna have it. Now, using your laptop or desktop, just put EI function, Google it, and you will have more information, a lot of information of EI function. However, EI function, EI what? EI, let me say EI x, EI minus x. What is x? X is 4D squared divided by 4TD. This is x, see? This is x. What is x? 4D squared divided by RD squared divided by 4TD. Sorry, RD squared divided by 4TD. Now, this EI function can be obtained from the integration from x to infinity, 1 over mu e2 minus mu d mu. See what I'm saying? The integration from x to infinity, 1 over mu e2 minus mu d mu. Okay? Now, what is mu? Mu, you can assume that mu equal to what? RD squared divided by 4TD. And then you can solve. Now, this solution, of course, is given by what? It's called Boltzmann transformation. Boltzmann transformation. By the way, you do not need to bother yourself with all of that, but I need you to know that. So it's not part of your responsibility to know that. I mean, do not give it that much time, but you need to know how can we develop the solutions from the divisivity equation? You do not need to know exactly what does it mean Boltzmann transformation, but you know, you have to know that. Okay. Now, what is x? As I said, x is the function of EI. So the function of EI is 4d squared divided by 4td. Now, what is RD? RD, we're going to change it to what? To real-time units. What is RD? RD, guys, as you remember, RD, what is RD? R divided by what? RW. See what I'm saying? So we're going to remove RD and put R divided by RW. So this is square and this is square. See what I'm saying? And what we have here, we have TD. And instead of TD, what we are going to put? Instead of TD, what we are going to put? We are going to put what? 0.002637 K. This is permeability, T, divided by what? Phi, porosity, mu, and C sub T. See? So we're going to put it here. Now, solve for x, then what you will have? You will have this model. Because phi mu C, they're gonna move up. 1 divided by 263 gonna give you 948 phi mu CT. R square, here's R square. KT, and RW gonna go what? Gonna go with RW square here. See? RW gonna go with this one. So here is x, guys. So this is x. Please give your attention to x. What is x? You have to know that x is 948 phi mu CT R square divided by KT. So x is a function of what? X is a function of what? X is a function of R square, the distance of the point from the wellbore. And of course, it's a function of t. So x could change with what? X could change with space or time, t. If you know x, then you are going to put x where? You're going to put x here. See? And then you can come to the integration and get the value of EI function. When you get the value of EI function, then you can get back here and calculate the pressure in dimensionless form because it is minus half EI function. So you will have the value of what? You will have the value of the pressure distribution given to you in dimensionless form. Can you change it to real-time pressure difference? Yes, of course. Because if you get back to BD, what's the definition of BD? BD is what? KH divided by 141.2 Q nu V divided delta V. So you just change del BD to real-time pressure difference delta V. To do that, you need to know what? How much B sub D. To know how much B sub D, you need to know how much the EI function. To know how much the EI function, you need to know how much the value of X. To know the value of X, you need to know R, you need to know T. Is that clear so far, guys? Is that clear?
Sir, the aim is not clear, the aim of this explanation.
What's that? Sorry?
The aim, the idea behind this diffusivity equation, like it's not clear still. We don't know what we are doing this for what.
Okay. Wait. Listen, we have not started. This is the point. Now, is it clear? Let me say, I'm not gonna say clear because you don't know how can we get this one. But what you need to know, guys, let me show you. This is our divisivity equation. See, this is our divisivity equation, 1111. 1111. This model can be solved using the line source to get this one. Okay, is that clear? Do not tell me how. This is not part of your job now. But 1111 can be solved to give you what? To give you 1112. Okay. Have you taken differential equation in the third year? Guys, have you taken math differential equation in the third year?
Have you? Sir, we are taking advanced. We are taking it now.
Oh, you are taking it. Oh, okay. No. Yeah. Okay.
You have just started.
Yeah. Listen. Uh, Again, this is my point of view. I believe that work test analysis should be given to fourth year, not the third year, because of that. Because we're gonna work with advanced mathematical models, so it should be taken first. Then we can go to the work test analysis. Now, why it is given to you in the third year, I don't know why, but I mean, in my university, it is given to the fourth year. See what I'm saying? However, so I do not need to bother you with a lot of mathematical formulation. But what you need to know that equation 1111, this is the solution. This model is developed from equation 1111. How? It's not part of your job. If you need more information how to develop this model, I can explain it to you, but it is not required from you. Is it clear?
Yes, sir.
Okay. So, okay, let us forget the divisivity equation. Now, this is the solution. Now, we're going to stick with the solution. This is the solution given to us. This is for line source. Again, this is for line source. We have point source. We have a plane source. A plane source for fractured formations. Plane source for fractured formations. See what I'm saying? So, more complicated from the line source. But now what we need line source solution. So this is the line source for the divisivity equation. Now we need to understand this one more. How can we make this one applicable? Here is the point. This is what I'm going to explain it to you, hopefully this week or the coming week. See what I'm saying? So please be patient with me. Be patient. Stay with me, and you will know why we need to move all of that. Okay? Okay. So this is the model that gives you the pressure distribution in dimensionless form for a point located at a distance RD at a time called TD. Okay, and for RD, TD, both of them a function of what? Wellbore radius, R, the distance, and the time. Okay. Now, in the literature, you're gonna find some of the ready-made solutions for this model. For example, one of them shown in Figure 111. See, this is line source solution for finite wellbore radius. Okay. So this figure is designed for different R sub D, starting from 1, going to 1.1, 1.2, until 20. So again, what is R sub D, guys? R sub D, again, R sub D is R, that is the distance at any point, to RW. See, the distance to RW. Now, when RD is 1, it means that R equal to RW. When RD is 1, it means that R equal to RW. So where are we in this case? We are in the wellbore. So in this case, if we are in the wellbore, the pressure is going to change with T like this. See? But for a point located at some distance in the porous media, so that R sub D is 1.1, which means that R is greater than RW by 1.1, the pressure is going to be changed with this line. See? And this one for 1.2. See? And this one for 1.3, and so on until 20. Okay? So let me give me please 1 minute. Let me check the first part just to be sure that is saved very well. Let me check that. Okay. Yes, it is. So copy. Let me put it. Okay, it is saved now. The first part is saved now. I'm going to continue with you guys, okay? So here's one of the solutions. This figure 1.1, shows you some of the solutions for the pressure distribution using different RD at different times. Now, what can you tell me, guys? If you look carefully at this figure 1.1, what can you tell me about the pressure behavior after long production time? This is long production time here. This is long production time here. See? Long production time here. So this shape gives us an idea that the pressure distribution is not going to change at late production time, regardless the distance of the point from the wellbore. So what I'm saying, the pressure distribution is going to be the same at late production time for different R sub D. So at some time, there will be no impact for the distance from the wellbore. There will be only the impact of the time. This is what we can infer from the shape of the pressure behavior given to us in figure 1.1.1. Okay. We are reaching the application that could be more understood for you. Now, here's what we have, guys. Going back to the EI function given to us in equation 1.1.12, the EI function. Now, how can we solve the EI function without going to the integration process? Can we solve the EI function? Yes, of course, we can solve the EI function. Now, what we have, the EI function, we do have three solutions to the EI function. Give me your attention, please. We have three solutions to the EI function. One of them, when x less than or equal to 0.01. See, this is the most important one. When x less than 0.01. Now, what is x? Do you remember what is x, guys? Again, that's what I need you to know. X is what? 9, 4, 8, 5 mu CT divided by what? KT. See? Sorry, KR. I think KR. Let me check it. X, okay. Yeah, here is X. See? 9, 4, 5 mu CT. Yes, KT. 5 mu CTR. 5 mu CTR. So, when X is less than or equal to 0.01, we're going to go with what is called logarithmic approximation. We're going to go with what? It is called logarithmic approximation. What is that? We can say that the I function here is see, this is the logarithmic approximation. See, the EI function is ln, see, ln TD divided by RD square plus 0.80907. This is the logarithmic approximation. Let me repeat this point because this is important. When x less than 0.01, when x less than 0.01, then you are going to go with what? The logarithmic approximation. For what? For the I function. When x less than 0.01, you're going to go with the logarithmic approximation for EI function. So EI function will be written like what? TD ln TD divided by RD square plus 0.80907. Is that clear so far, guys, what I'm saying here? Is that clear so far? Is it clear to you guys? Hello? Hello? Hello?
Yes,
Do you hear me?
Yes.
Where are you? Okay. So when x less than 0.01, the I function can be estimated using the logarithmic approximation. What is that? The I function is going to be ln TD divided by RD square plus 0.80907. So in this case, the pressure can be written in this shape. So basically, if you get back to the solution, you are going to find minus half EI function minus RD squared divided by 4TD. So you're going to remove the EI function and you're going to put this one, ln TD RD squared plus 0.80907 times minus half, minus with minus gone. So what we will have, half ln TD RD squared plus 0.80907. So this is the solution actually. This solution is used when the value of x is less than 0.01. Okay. How about if x is greater than 0.01? Now we have two options. If x is greater than 0.01, if x is greater than 0.01, less than 1, greater than 0.01, less than 1, or sometimes it could be less than 3, then you're going to go with this model. You're going to go with this model. See, here is the model. And what you have, A1, A2, A3, A4, of course, x. What is x? We know x is 948 mu CT divided by R squared divided by KT. A1 is given here, A2, these are the 8 constants. See? This is the second option. If x greater than 0.01, less than, let me say less than 3. Okay. How about the case if x greater than 3? The EI function in this case will be what? Will be 0. The EI function in this case will be 0. So three options for the EI function. One of them, if x is less than 0.01, then we're going to go with what? Logarithmic approximation. If x between 0.01 and 3, we're going to go with this model. If x greater than 3, the EI function is 0. Now we are going to go to the second disconnection. Please rejoin me again when we will have the second disconnection. While I am going to...
Sir, we only have 4 minutes.
No, why?
Stop, you have another class.
Oh, yes.
Well, testing is finished.
Oh, okay. Okay, so we are done.
You have natural gas.
Yes, sorry for that, because I thought 3 hours. Yes. Yeah, so, okay, done. When we will have the disconnection, we have finished, okay? So you can... Do you have questions?
No, sir.
Okay, you can leave.
Sir,
Yes.
Sir, I haven't recorded. If you can, please send it to me.
Yes, of course, I will do that. Okay?